Okay, before we continue, let's restate the problem that we are trying to solve. We have a unit square like this. Let me see whether this is better. And we have n points inside this square. And for each line that pass through two of these points, okay, there are going to be, now we can assume, we don't need to consider degenerate cases yet. No three points on the same line. We can say at most 2 points are on the same line. So there are going to be n square such lines. Okay, if we have n points, there are going to be n times n minus 1 divided by 2 such lines that pass through these two of these points. Now we are given these n points and these O(n) square lines, and our goal is to compute the number of points below each of these lines. So how many of the, if you exclude these 2 points, how many of the remaining points are below this line? I mean, same, if you compute the points below this line, you already know the ones that are above it. You know the total number, okay? So computing the number of points below it is sufficient. So our goal is there's the obvious solution. So this is the problem we are going to solve. So for these n square line segments, we are going to determine for each of them how many points are below this these lines. And the obvious solution we have talked about is for each of these n square lines, you can check each of the remaining n points, which of them are above, which of them are below. So in O(n) time, you can do this check. So the total algorithm becomes O(n) cube. Now, we are going to see a solution which can do this in O(n) square time. We are going to reduce this to the number of line segments we have. So for each of these line segments, we are going to determine how many points are below it, how many points are above them. Now to solve, so this is the problem is now reduced to this form, the supersampling and ray tracing. This is the problem that we are going to be dealing with for the rest of today. Now, the solution to this seems really difficult in this setting. I mean, how can you? Take a single line, for example. It's like impossible to find out how many points are below it and above it in one time. So obviously the solution is not going to process each line separately. We need to see some coherency between, for example, some neighboring lines. For example, when a line, so these neighboring lines, they have some related they are above and below points, probably they are similar to each other. We need to make use of something like this. But even in that setting, the neighboring lines idea is really difficult because these n square lines, they're all intersecting with each other. There's no order with them. There are n square intersections among them again. So it's really, what we have here is a really complex structure. So the neighboring line idea is even very difficult to implement in this setting. Now, a common technique in computational geometry is that, it's not always the plane sweep technique we use, okay? So this time we are not going to do plane sweep, no plane sweep. Now, the other common approach in computational geometry is looking at the dual problem. So the dual problem, so what is duality? There are dualities in different settings. For example, the Delaunay triangulation was the dual of the Voronoi diagram. Okay, so we have seen duality actually before. So by computing the Voronoi diagram, you could compute, if you take the dual of it, you can find the Delaunay triangulation. Also, we talked about for triangulations, we looked at the dual graph. in which each triangle is now the node, and there's a vertex between them if these two triangles are neighbors. So we have seen duality in some context, but now we are going to see in a different setting. Consider a point in 2D, which is given by 2 coordinates. Now, we also consider also a line in 2D. A line is also, and ignore about vertical lines, we can deal with them in a different way, but any line which is not vertical can also be represented by 2 parameters, right? We have a line y is equal to mx plus b. This m and b parameters, I mean any 2 values, any 2 parameters also define a line, okay? So the duality transform is this point. If we transform, can we transform this point to a line by having these 2 values, treating them as if this one is slope and this one is the intercept, for example. So one way to do this transform is that, I don't know why they've chosen this way, but one way to do is, I mean, this minus y could have been plus y, but it will have different properties if we do that probably. So one transform is that we can transform this point to a, let's name it point star, which is equal to this line in another plane. This one, the point where the point exists is called the primal plane, and this is in the dual plane. This point becomes a line. So all the points in the primal plane can be converted to lines in the dual plane. Okay, so every point can be considered as a line when we do this duality transform. And similarly, if we had a line in the primal plane, which was mx plus b, okay, if we had a line here, similarly, we could what it would transform is that the duality, if we apply the duality transform to this one, it would become a point. So each lines in the original plane, we turn them into points, and each point is turned into lines. Okay, so a line like this, it's going to be its duality transform is going to be a point, which is m minus b. Okay, so a point m minus b is a line is going to turn into a point, and each point is going to turn into a line. So why do we do this? Just to try to get a different perspective to the same problem. Okay, now remember the original problem was finding the number of points below a line. Okay, now this turns out these points, they become lines, and this line become a point. So it's finding the number of lines above a point. So it becomes, our line here is turned into a point. These become line segments, but finding lines above a point, again, it's not a very simple problem. I mean, this different perspective, we still need to work out some details in order to see whether we can solve this. But such transformations, their main purpose is to get a different perspective to the same problem. Maybe in this different perspective, you could solve the problem much easier. Okay, so this is the main idea. We are trying to find a solution, looking for a solution, and such a duality transform may make it easier to see some things. And now I'm going to talk about some properties of this duality transform. For example, one important property is that if a point is on a line, so if this is P, which is equal to Px Py, okay, and this is the line. If we have a line which is equal to mx plus b, if this point is an element of this line, if this point is on the line on the primal plane, in the dual transform, the line is going to be a point on the dual of this P star. So in other words, if and only if in the primal transform. So the incidence property, so if the point is incident on a line, the transformation of that line, which is now a point, is going to be incident to the P star, which is going to be the line in the dual transform. And this property also makes it really interesting. If we have 2 points on the same line, okay, so this is P1, this is P2, okay, if they're on the same line, what happens is that, what happens in the dual transform? Both P1 and P2 becomes lines, so what L becomes? It becomes their intersection, right? So L becomes their intersection, so this a point, a line that passes through these 2 points becomes an intersection point in the duality transform. So this line that we were looking for that passes through 2 points is going to, I mean, this was not a very much, I mean, understanding the relationship between these lines were not very easy in this setting. I mean, there were several lines that passed through these points. They were lines, but in the dual transform, they are going to be vertices. Each of these lines that pass through these points are going to be vertices. They are going to be the intersection points of these 2 line segments. So this is the incidence property. Let me also... Yeah, they have the different coordinates. They are going to be different lines. But only if 2 points have the same x coordinate, it means that they are going to be parallel lines. Their dual transform are going to be parallel lines. Their intersection is not going to be defined. If 2 points here in the original primal plane, if they have the same x coordinate, I mean, it's obvious because if we draw the line that passed through these points, it's undefined. So it's a vertical line. We cannot write a vertical line in terms of y is equal to mx plus 1 because m is infinity. Okay, so therefore the duality transform for vertical lines is not defined. And since this being undefined is seen as the fact that points which have the same x coordinate appear as parallel lines. So they don't have an intersection point. Okay, so it's really good that why it is undefined. So they don't intersect. So the line does not have a dual transform. It doesn't exist because those 2 lines, they appear as parallel lines. So let me draw in order to show you some other properties. Let me draw this figure in the book, figure 8.2. So I have the x and y coordinates and 3 points. P1, P2, P3, and this is L, and I have P4 here. And this is primal plane, and dual plane. In dual plane, we are going to have again the x and y. Now, this is L star. This is P1 star. P3 star and P2 star, and this is P4 star. Okay. Now let's look at this. So this was, we had 4 points and a line that passes through 3 of them. Since this line passes through 3 of them, it's going to be intersecting these three lines. It's going to be at the intersection point of these three lines. And it's going to be on the x-axis because line L is also intersecting the x-axis. Okay, so it's going to be intersecting it's going to be on the x-axis. Y is equal to 0. And now we have already seen the incidence property. If the points are on the line is going to be the transformation of this line, which is a point, is going to be on the transformation, the duals of these points. Now, there's another interesting thing, which is, let's look at this point 4. In this point 4, which is above the, so now we are going to think about the relationship between a line and a point. Okay, given a point and a line, which can we say whether the point is above or below the line? So we need to define a certain relationship. Which half plane is above? Which half plane is below the line? So we need to define uniquely, be able to define uniquely below and above. So for vertical lines, the below and above is undefined. So both, since it's dividing as a vertical line the whole plane, there's no below-above relationship between these two half planes. But for any line with a positive slope, what happens is that this part is going to be the above of that line, okay? And this part is going to be the below of that line. And for a line with negative slope, if we move this line towards here, this part is going to be the above of the line, this part is going. So for any line, we can actually, for any non-vertical line, we can uniquely find where is below, where is above this line. Okay, so here we can see that P4 is above line L in the primal plane. So the order, so there's also the other important, the order preserving property of the duality transform is that if P4 is above L in the primal plane, the point L is above P4 in the dual. So it's like reverse actually. It's like we say order preserving, but it's like the reverse of what happens here. P4 is above L here. Here the point L, so it's order preserving because here now, I mean, again, now the points are always above, okay? So you can, if you consider it like this, the point is again, now this L star is going to be the point. The point is going to be above the line P4, okay? So this order is also preserved. If P4 is above L, L star is going to be above P4 star in the dual plane. So this is called the order preserving property of things. So what happens is that, now let's get back to our problem. We were trying to find the points that are below a line, right? So what happens is that, so these are, so this is the below. So these points are going to be lines which are above this, so this L is going to be a point, L star is going to be a vertex in the dual transform. And these points that are below it are going to be transformed into lines that are above this L star. Okay, so this is due to the order preserving property, we can actually now, thanks to this order preserving property, we can now transform our whole problem into the dual plane. Now, in the dual plane, we are going to ask this question. We have n points here. We are going to have n lines. Each point is going to transform into a line. Okay, so we are going to have n lines in the dual plane. Since we have these sample points, n of them, each of them transforming to a line, we are going to have n lines in the dual plane. And lines that pass through two of these points are going to be the vertices in this arrangement of lines. So we are going to have an arrangement, a line arrangement. This is called, if we have a set of n lines in the plane, this becomes an arrangement of lines. Okay, we have, so how can we represent, we have n lines. Can we represent these n lines, for example, they are going to divide the plane into faces. We are going to, so we can actually think about it like a doubly connected edge list. If you have these n lines, the intersection of two lines is going to be a vertex, and that vertex is going to correspond to a line here. Okay, now this line, which is not the relationship between these lines are not very apparent here, but in the dual transform plane, what we are going to see is that each of these lines that pass through these pair of points is going to appear as a vertex. So these vertices, for example, they may be incident on the same face. They may be two different endpoints of an edge. Okay, so our line segments are going to become a much more apparent structure. They are going to be vertices in a doubly connected edge list. And the problem is going to be about, given this doubly connected edge list and given a vertex, how many lines are above this vertex. Okay, if you can compute for each vertex how many lines of the doubly connected edge list are above this vertex, you solve the problem of how many points are below it in of this line segment. Okay, it becomes the same in this dual transform problem. We try to solve, given a vertex in this line arrangement, how many lines are above it. Okay, so we are going to solve this problem next. We are going to first, in order to solve this problem efficiently, still. I mean, if you try to solve the problem in this setting without using any data structure, again, it's going to take O(n) time per vertex. Okay, so there are n square vertices. For each vertex, if you check each line whether it's above or below it, again, this takes O(n) time. So the total time is again O(n) cube. Okay, looking from this perspective, we didn't still reduce the n cube to n square. We are still at n cube. For if we process each vertex separately and try to find out each line whether it's above or below it, we are still solving the same problem. But now what we are going to do is, these arrangement of lines, this set of lines we have in the plane, we are going to create a data structure for them. We are going to identify the vertices, the faces. So the next thing to solve the problem is, we are going to create the subdivision induced by these arrangements, by these sets of lines. This is called an arrangement of lines. An arrangement of different objects, different geometrical objects are encountered in different computational geometry problems. So what we have here is that, and so an arrangement of lines is called a simple arrangement if no three lines or more lines pass through the same point. Okay, I mean at most two lines intersect at a point, and no two lines are parallel. Okay, so if we have an arbitrary set of lines in which no two lines are parallel and no more than two lines pass through the same point, what we have is a simple arrangement of lines. And in this simple arrangement, we are going to have exactly n times n minus 1 divided by 2 vertices. So this if you treat it as a doubly connected edge list, we are going to have that many vertices, n times n minus 1 divided by 2. And the number of edges are going to be exactly n square. Because each, if you remember, on a line, for example, this line is going to be intersected by n minus 1 lines. Okay? If I have n minus 1 vertices on this line, I'm going to have n edges. Okay, so the number of vertices, if for example it intersects 3 here, I have 1, 2, 3, 4 edges. So it's 1 plus the number of lines that intersected. So for each line, I'm going to have n edges. Since I have n such lines, it's going to be n square, exactly n square edges in the doubly connected edge list. But we need to take care of this arrangement of lines, possibly have unbounded faces and infinite edges, right? And doubly connected edges cannot handle these. I mean, our edge records have 2 vertices beginning, and so we need to have a finite, and again we solve this problem by bounding it with a bounding box But this bounding box, what is going to be? Our lines are infinite. So any ideas? So we have lines that extend to infinity, okay, in every direction, and we are going to create a doubly connected edge list for these lines, and we want to put a bounding box around them. So what is the natural way to put this bounding box? Since we are interested in the intersections, a bounding box which includes all the intersections would do fine, right? And this can be, such a bounding box can be found in O(n) square time by looking at all the n square intersections, finding the bottom intersection point, top intersection point, left and right intersection point. We can create a bounding box to ourselves which contains all the intersections of these line segments within itself. Okay, so this is going to bound the infinite edges, and infinite unbounded faces are going to be bounded like this with this bounding box. It can be done. We can compute this bounding box in n square time. Now, so we have n lines and we have the 4 edges of the bounding box in this new dual transform. So let me draw the dual transform of this problem. So we are going to have a bounding box, and in it we are going to have the intersections are going to be within that. For example, it's really difficult to have all the so I'm just going to stop here with three lines because it's difficult to have all the intersections within this bounding box. If I draw something here, for example, the intersection may occur here, okay? But we can, we found this bounding box after we have the lines, so we can first find all the intersections and find the bounding box which encapsulates all of them. Now, this is what we have. We are only going to be interested in this region within the bounding box, which contains all the n square intersections. Now, can we, given these, this is an arrangement of lines, okay? We have lines, this is an arrangement of lines, and each of these lines actually correspond to a point here, okay? So in this, we transform all the points to lines, so we have n lines here. Now, the next thing is to construct a data structure. How can we construct a doubly connected edge list given these line segments? Actually, they become now line segments. Since they are bounded by this bounding box, they become line segments, and finding the doubly connected edge list for line segments, we have seen this in chapter 2 actually. The first time when we see the overlay of subdivisions and the doubly connected edge list, the first time they appear was in line segment intersection problem. And in line segment intersection problem, we created a doubly connected edge list for the intersecting line segments at the end. And if you remember the complexity, it was n log n plus I log n. I was the number of intersections. Here, if we can use that plane sweep algorithm to construct the doubly connected edge list for this one, but the problem is that the number of intersections is n square. So we are going to have n square log n. We can construct this doubly connected edge list by using that technique in n square log n time, since we have n square intersections. But we are going to see an incremental algorithm now, which is better than the plane sweep algorithm. We will be able to construct this in n square time in total. So the whole doubly connected edge list for n lines like this, a simple arrangement, or it doesn't need to be simple arrangement. We can actually handle lines that pass through, 3 lines passing through the same point can also be handled by this algorithm. Okay, we are not going to consider parallel lines. We can actually treat them separately in the primal plane. For endpoints, there are a linear number of vertical lines that pass through these endpoints. Okay, I mean there are that many different x coordinates. If you have endpoints, there are at most n different x coordinates. If 2 of them share a single x coordinate, this number is going to be reduced by 1. So there are there are linear number of vertical points. Since there are linear number of them, there are O(n) such vertical lines. For each of them, you can check whether which points are to the left of it or to the right of it in ON time. So in ON square time, you can handle the vertical lines. Okay, so we are not going to treat vertical. We are not going to consider vertical lines. We are going to assume that they are treated in a separate algorithm, which also takes ON square time in total. So we don't have parallel lines here in our arrangement. We don't have parallel lines, but so we may have if 3 points are collinear. We may have more than one line passing through the same vertex. Okay, we can have this situation. Now, how can we construct the doubly connected edge list for this arrangement of lines in ON square? This is we are going to see next. And this is the algorithm I'm going to describe is an incremental algorithm. We are going to add each line one by one, and the invariant of this algorithm is that if when we add line Li, for example, if the lines are ordered from L1 to Ln, when we are adding Li, the arrangement of all the lines up to Li minus 1 is a correct doubly connected edge list, is constructed, okay? So we have a correct doubly connected edge list for the lines inserted up to now. So we have a correct doubly connected edge list, and we are inserting a new line to this doubly connected edge list. What will happen? How are we going to update this doubly connected edge list? Now, when a new line enters here, like this, consider this black line, which just entered this doubly connected edge list. And what happens is that only the faces which are intersected by this line need to be updated. Okay, only this line splits the faces that it intersects. So it's this face, and this face here. 3 faces are going to be split into 2. And this is all I need to do. I need to update in order to have the correct doubly connected edge list for the for after adding Li. I need to update my structure, data structure, to have these faces split. Now, how are you going to determine which faces they? Are you going to do intersection test for each face, which is at the end also going to be at the end, it's going to it's ON for each of them. It's not going to be ON square in total, right? Because the face intersection with faces, you may have n square faces. If you remember, also I didn't mention that we have n square vertices, n square ON square edges. Also, if you use the Euler's theorem, you are going to see that the number of faces can also be quadratic. Okay, so the number of faces at a certain time, you may have n square different faces. So intersection test with all the faces is going to give you an ON cube algorithm at the end. But what we can do is, here is the strategy that we are going to use. We are going to make use of the doubly connected edge list that exists, gives us some information. For example, when we intersect this face, the next face that this line intersects is a neighbor of this face, right? So we are going to use this, and this neighborhood information is in the doubly connected edge list. I mean, we don't have face neighbors, but we can continue, we can traverse the edge records. We have the next edge record. So for example, what we do, we need to maybe first show that each of these the intersection, actually we have shown that the intersection of half planes, the faces are convex regions. So when this line intersects a face, it's going to intersect 2 edges of that face. Now we enter through an edge by traversing. So if this is the counterclockwise. So this is the half edge that we intersected. Okay. If we find the half edge that is intersected, we can find the other half edge which is intersected by following these next records. We are going to check whether the next edge is intersecting, or if not, we continue towards next. And at one point, we are going to find out which point this line exits that face. So we are going to, after we identify an entrance to that face, we can find the exit from that face by following these edge records. Now, the good thing about this is when we exit this face, what we do, we enter the next face. Through which edge? Through the twin, through the twin of that half edge. So it's already given, so we don't need to do, it's like linear traversal of this doubly connected edge list. When this twin of this one is going to be the next edge that we enter through, and we are going to continue following these. Now, here's something interesting. When we come here, at this point, there are multiple, so here, we are at this vertex actually, not this edge. At this half edge, we see that we intersect the vertex of this face. So, and in this vertex, what we need to do is, we can find out, this was in your homework too, I guess, all the incident faces are actually traversed in clockwise order. I mean, if you follow the next twin type of thing, if after you're on this vertex, you can traverse all the edges that are incident, we don't have this right now, to this vertex, and actually find out whether you are intersecting this face, F1 or F2. Okay, so we need to do a traversal around this vertex which is shared by multiple faces and determine which face actually is intersected by this. And this can be done by, incrementing this a delta amount and checking whether this is the one we are going to be inside or this is the one we are going to be inside. Again, after we determine that this is the face that we are intersected, this is the edge that we are going to consider. Okay, so this is that edge. We are going to continue traversing its edges until we see which edge we exit through. Now, this traversal, during this traversal, we find which faces we split. Now, the question is, the number of faces that we visit, or even considering these vertices with multiple degrees, considering this, how many faces, how many edge records do we visit? Is it a quadratic number or a linear number? If we can bound the number of faces and edge records that we visit by a linear bound, it means that for each line, we do a linear number of operations, and at the end, inserting n lines, we can construct this doubly connected edge list in O(n) square time in total. Okay, so we can reduce this n square log n plane sweep algorithm to an O(n) square algorithm by using this strategy, traversing the edges and traversing the faces. And the theorem is called the zone theorem. Okay, this theorem that bounds the number of, that bounds the complexity of the things that we visited by a line is called the zone theorem. So the zone of a line that passes through a subdivision is all the faces, is the union of all the faces that are incident to this line at some point. So for this vertex, we are going to, so the zone of this line is going to be this face, this face, this face, this face, this face. Okay, so whenever, if we are incident to a face, even at one vertex, or if we pass through it, so there are two cases. If either we are incident, this line is going to be incident to a face when it passes through it, or maybe it's passing through a vertex of this face. Okay, so this at this point, for example, this line is incident to this one and this one and this one and this one. So it's going to be, these faces are going to be included in the zone of that line. And this theorem says that if there are, if the complexity of the subdivision, or let's say if there are m vertices or m lines, so let me read the theorem. Yeah, m lines. If you have m lines, okay, the complexity of the zone of a line that passes through the arrangement of these m lines is OM. Okay, so it's bounded linearly. So if you have n lines, if a line passes through these, it's not going to intersect n square faces. It's going to intersect with ON faces. So, and if making use of the next pointers, these you can visit all the faces. Here, what you do is you do not, during this traversal, you do not get out of the zone of the line any time. Okay, you are always within the zone of that line during this traversal. Since this zone is bounded by a linear number, for inserting each line here is going to take linear time. So inserting a line incrementally is going to take OI time actually. So for inserting the ith line, it's going to take OI minus 1 time. Okay. So in total, we are going to create the doubly connected edge list in ON square time. Okay, so this is given points in the plane, we transform them to lines, and for these lines, we construct a doubly connected edge list in ON square time. Right now, we didn't yet solve our problem. How many lines are above vertex? We haven't solved this problem yet. But after we have the doubly connected edge list, we'll be able to solve this easily. Again, for n square vertices, we are going to determine how many lines are above these n square vertices in ON square time. Okay, so this is now the next thing I'm going to show you is that how do we, given a doubly connected edge list, how many lines are above a vertex? How do we compute this efficiently? So this is called we are going to define a term which is called the level of a vertex. So for that, let me draw something. And the level of a vertex is the number that we are trying to find. The level of a vertex is in a subdivision is going to be the number of lines that are above that vertex. If we can compute the levels of all vertices in ON square time, it means that we have find out for each vertex how many lines are above it in total ON square time. Okay, any questions about doubly connected edge list construction of line arrangements? Okay, what I didn't discuss in detail is that when we are splitting a face, how do we update the edge records? So what happens when we, but these are not, this is not very difficult. What we do is we add a new pair of half edges for the line segment which is inside that face. Okay, so for the intersection of this face with that line, after we determine the entrance and exit points, we create two half edge records, a pair of half edges for the part which is inside this face. And also these edges which are intersected are divided into two as well. So we divide two edges into two pairs of half edges. This one is divided into two pairs of half edges. This is also divided into two pairs of half edges. And we create vertex records. At these intersection points, we create new vertex records. And we create this new half edge, pairs of half edges. And when we pass through a vertex, we don't create any vertex records. We don't divide any existing edge into two. Okay, when we pass through a vertex, that's easy to update. All we need to do is add this new pair of half edges and nothing more. Okay, add these incident. We also need to delete the existing face. The whole face is deleted and replaced with the split, the new two faces, okay? And we also set the incident face records of each half edge accordingly. Still, in terms of programming, it's not very easy. I mean, you need to adjust a lot of half edge records, face records, create new records, and update delete something from the face records. So during this construction, your doubly connected edge list should be capable of these insertions and deletions efficiently. Inserting a face, removing a face, inserting an edge, removing an edge. So you need to have an efficient way of, instead of having them as linear tables, maybe you can have a different, like a tree structure or like a hash table, I don't know, but you can have an efficient way to store the faces and edges. Now, let's come to our original problem, again, what we were trying to solve. Given this doubly connected edges, we wonder, for each vertex, how many lines are above a given vertex in this doubly connected edge list. So this was, if we can solve this problem, it means that we have, for each line segment that passes through 2 points, how many points are above it. So we are going to solve our original problem with that. So let's define the level concept for that. So let me draw the, so these are like 2 parallel ones. And there is another one here. Okay, so now these are my vertices. Okay, now for each vertex, I define the level of that vertex as the number of lines that are strictly above it. Okay, so for this point, there is no line that is above it, so its level is going to be 0. And for this one, there is this line, and its level is going to be 1. And for example, let's look at this one. How many lines are above it? For this vertex, this one is above it, this one is above it, and there are 3 of them. Let me check, I'm counting right. Yes, so there are 3 lines that are above this vertex. So let's look at this vertex again. This one, let me mark them with this X signs. This one, and this one are above this line. So again, let me remind you, this above and below relationship is uniquely defined between a point and a line, okay? So for example, for this line, its below is this part, okay? So for a vertical line like this, above, below is undefined. We have left and right. So if the line becomes like this part is below, this part is above. And if the line is like this part is above, this part is below. Okay, so it's uniquely defined for each line. And we can determine whether a point lies in which region. So for this vertex, this one, and this one is above that line. And for this vertex, what we have is that this one is also now the newly marked one. This one becomes strictly above that vertex as well, and all the other marked ones were already above it, so its level is 4. So the level of a vertex is the number of lines that are above it. Now here is how we are computing. So if we can compute the levels of all the vertices in our doubly connected edge list, we solve the problem, okay? It gives us how many lines are above each point. In other words, how many points are below each line segment. So remember, each of these vertices, again, they correspond to lines that pass through 2 points in our original problem. Now, here's how we do it. First of all, we find for each line. So here, this doubly connected edge list is constructed by using lines, right? So pick a line here. I mean, get back to the original problem. Pick a line and find its corresponding edge here. For example, this line here, its leftmost vertex is this one. So for a line, and for its leftmost vertex, we spent O(n) time to find how many lines are above it. Okay, for the leftmost vertex, we spent the naive exhaustive time. For this leftmost vertex, we find out how many lines are above this vertex. And we can do it by looking at all the remaining n-1 lines. We look at remaining n-1 lines and find out how many of them are above this leftmost intersection point. We spend O(n) time doing that. And what we do is, by following the previous and edge, we can follow all the vertices along this line. Let me also draw the other figure, which is going to help again. So let me tell you before actually drawing it. So by going through all the vertices one by one, what will happen is that at a vertex, a line passes through this vertex. And this line either may come from above or it may come from below. So during this intersection, during the next vertex, we are going to either increase our level or decrease our level. So this is the neighboring vertices, the coherency. Here is how we can use the coherency. The neighboring vertices are going to have similar levels. When we are from here 3 to 4, what happens is that this one at this vertex here, at this point, I mean here it's 3, and all the points here are going to be actually 4 at that point. Okay, actually I can find out that at this point I leave it at 3, but I know that any vertex that is going to come, any point that comes after that is going to be below that. So consider any point on this line. This vertex, I mean this line here, which was producing this vertex, we were counting the lines strictly above this line, right? So at this point, we don't count this line as a line that is above it. But this line here, any point to the right of it is going to be below this line, right? So at this point, right after we pass this vertex, we increase our level to 4. Now at this point, what happens at this point, again, right after this point, all the points here are going to be again below this one. So at this point, it increases to 5. So this one should be 5. This vertex should be 5. Let me check if I'm correct. Actually, there is another. Okay, now here, this is an intersection. So this one, so let's see. And at this point, so let's take a point here. Still I have, so 1, this one is above it, this one is above it, this one is above it, 3, 4, 5. So actually all the points on this line, I have any point on this line, their level is going to be 5. But when we come to this point, we see that these two lines cease to be, since these two lines define this vertex, they cease to be above this point. So it's going to be 5 minus 2, it's going to be 3. Okay, so these two lines which are incident on them, and by looking whether a line is coming from above or below, we can actually find out whether we are going to increase or decrease the vertex level while we are going on this doubly connected edgeless, going from vertex to vertex in this doubly connected edgeless. We are going to either increment, if this is a simple arrangement, no 3 lines are going to pass through the same point. If it's a simple arrangement, each time we are at a vertex, it's going to either decrease or increase by 1. Okay, we can prove that for if it's an intersection of 2 lines, that if each vertex is an intersection of exactly 2 lines, at each vertex, it's either going to stay the same, or it's going to increase by 1, or decrease by 1. So let's draw the last figure in the book. So in other words, by traversal, we first spend O(n) time to find the initial level of the leftmost vertex, and all the remaining vertices can be found in each of them is going to take O(1) time. Okay, we are either going to increase or decrease by 1, and we are going to have n vertices along this line, since a line is going to be intersected by n minus 1 other lines. We have n vertices along this line, and each of them is found by using O(1) operations. So we are going to have O(n) plus O(n) minus 1, okay, which is O(n). So we are going to spend this time to find the levels of vertices along a line. So it's in O(n) time. So in O(n) time, we are going to find the levels of all the vertices along a single line. Since we have n lines, the total complexity is going to be n squared. So in n squared time, O(n) squared time, we'll be able to manage to find the levels of all O(n) squared vertices in this arrangement. Yes? Exactly, exactly. Depending on how many lines intersect at that point. No, it's even at that assumption, since they intersect at this point, they're not going to intersect at another point. So the number of intersection points are going to decrease. Okay, so each line is going to be processed once. Okay, so we could have removed minus 10, but it means that we are going to process on n minus 10 intersection points along that line. So the complexity is not the number of vertices actually, it's the number of lines at each time. So it's not, we guarantee to spend n minus 1 steps for each line, regardless of how many vertices we have along that line. Okay, so this concludes our discussion. So in O(n) squared time, with the help of this duality transform, and since with the help of this duality transform, what we were able to do is, we were able to convert the set of points into a subdivision. Okay, our set of points which were disconnected, they were just a cloud of points. The cloud of points turned into a subdivision, an arrangement of lines, and we create a doubly connected edgeless for these arrangement of lines. And for each vertex, which corresponds to a line segment that passes through these 2 points, we found out how many points are strictly above it or below it by traversing this doubly connected edgeless. So doubly connected edgeless, again, so I mean, at the end of the course, if you forget everything, you shouldn't forget 3 things. Doubly connected edgeless, plane sweep, okay, and maybe the duality, because you are going to, in your programming assignment, you are going to make use of the duality property. Let me remind you your homework again, which is given 2 sets of objects, 2 different sets of objects in 2D plane, in 2 dimensions. The question is there a line that separates these 2 objects, the groups of 2 objects completely? Okay, you are going to write a program to find that. And there's an expected linear time solution to do this. So it's really good. It's like people have been using, like support vector machines they're linear separators. Okay, we are given in 2 dimensions, for example, if the machine learning, this is a classification problem. If you find this line is a classifier for you. For new objects, if your new object is above this line, you can classify it as one of the objects or the other type. So finding a classifier, and in support vector machines, this is a really costly process. You are doing a semi-definite programming optimization. Okay, it's an optimization problem, and it's really difficult. But with computational geometry, you can say that you can find a solution to this in O(n) time. Okay, there's the number of points. So finding a line that separates these 2, you can find it very efficiently by using computational geometry techniques. Okay, so this is going to be your homework. And I'm going to post the homework tonight, but I'm going to post the visualization helper program. So I'm going to also post a helper program visualizer to see your results, to see the set of points, and to see the line that you have found, whether you have found the line correctly or not. So it's a good way in these computational geometry problems. It's very good. It's really helpful to visualize the results you have found, because if your program just outputs 3x plus 5 as the line, it's really difficult to really see whether it's a separator or not. I mean, it's really inspecting it visually, oh, okay, it's separating the points or not. It's going to be very easy if you have a helper program. So I'm going to provide you that helper program, but you can start working on the assignment right away, okay, without the helper program. Just first think about how you are going to solve it, okay? So, but I gave you lots of hints today, so you'll be able to find the solution maybe in 10 or 15 minutes, okay? So the coding is not going to be that easy. The algorithms are already in the book, but still the coding is going to take some time. Okay, so that's it for today. If you don't have any questions, you can, if you want to see your midterm paper, you can come and see me right now. And I haven't graded your 5th homeworks yet. I'm going to do it in a week. So before next week, our next week's lecture, we are going to also learn your grades for the 5th homework. Okay, so see you next week. Next week, our plan is I want to skip the binary space partitions. Binary space partitions are already covered in computer graphics. So I'm not going to talk about binary space partitioning. And I'm going to go into more interesting topics. So next week I'm going to start a chapter about robot motion planning. So how can a robot find its way through a plane which has some obstacles in it. So we are going to see computational geometric techniques to solve this problem.